Cool. I'm going to try to speak loudly since we don't have a mic, but please stop me if I am too quiet. I'm Meghan Heintz. I'm a senior data scientist at BuzzFeed, but I primarily work on our Tasty property. And today I'm going to talk about Recipe2Vec, or how does my robot know what recipes are related. And just to give you a little context in case you don't know what Tasty is our kind of like mesmerizing, disembodied hand videos of people making different recipes. And within Tasty, we have a bunch of different sub-brands, like Tasty Vegetarian, which obviously for vegetarians, Tasty Junior for kids, Proper Tasty, which is our UK offering, not just British cuisine, just FYI, because I don't think there's that huge of a market for that. Also, Tasty Japan. This video is actually one of our Tasty Japan producers. I met with the producers of this video 3 days ago in Tokyo, so I am very jet lagged. If I fall asleep during this presentation, please throw something at me. Our content kind of falls into two different clusters, kind of like really easy, simple to make comfort food, stuff like 3-ingredient no-bake desserts, or like 1-pan chicken, or like 1-pot pasta dishes, things like that. And to steal some like Great British Bake Off terminology, showstoppers. So this is definitely like falls into our showstopper category. This is a jiggly, fluffy Japanese cheesecake. Very difficult to make. I've tried 3 times, and every time I come up with like a kind of sad, flat, sweet omelet. So unless you're a pro baker, I would like start somewhere else. So for the last couple of years, we've had like a really distributed social media strategy. BuzzFeed obviously is really into virality and being on Facebook, and in 2013 Facebook rolled out auto-playing videos. And we spent a lot of time observing what was doing well and kind of realized that probably their algorithm was optimizing for about 40-second videos. So we kind of looked at a bunch of different frames and then eventually ended up focusing on making 40-second recipe videos in that time. And we launched our Facebook page in 2015. This turned out to be a really good strategy for us because by 2016, we were the 4th most watched publisher on Facebook, like 1.8 billion views. Today, we've got 90 million fans on our Facebook page, and something like half of all millennials see a Tasty video every month. And then in addition to Facebook, of course, we're on YouTube and Snapchat and Instagram. And what we realized was 2 things: that we have this really nice like strategy for kind of shallow like consumption and like far reach, in that like we've got a lot of fans and a lot of people kind of know us a little bit. But for like our true like core power fans, people who are actually like going home and cooking these recipes, we really weren't like offering them that much. So you think about trying to cook something from a video you saw on Facebook, just even like going back and finding it after you have the ingredients is pretty difficult. You're kind of just like scrolling through feeds, or like on YouTube, it's a little bit better, but the search still isn't really optimized for finding recipes. So it can be like kind of a frictionful negative experience for people. We think that most people are kind of just watching these videos as like a relaxing, like bored at work network type of thing. But we saw from the comments that a lot of people were actually cooking them, because they would send us like modifications or tips for the recipes, or they would post pictures of the final result. So one of the things we realized is for the people who are actually cooking this, it was a really terrible experience finding the recipe, and then when you actually found it, we could see in our own video analytics that people were kind of scrubbing into the middle of videos and rewatching them, or just like putting them on repeat and watching them over and over and over again in one session. The second thing we realized is these aren't Tasty users. These are our Facebook users, YouTube users, Snapchat users, and Instagram users. At the end of the day, they are not our own users. So we know now that the like 40-second the algorithm is no longer like optimizing for this type of video, and that we're kind of like in kind of an unsustainable place, in that Facebook can kind of change their algorithm to do whatever they want. If you guys have been paying attention, about 2 months ago, they started testing in Eastern Europe this thing called the Explore feed that took all publisher content, put it in a completely separate feed, and then publishers from Eastern Europe said that they experienced about half the traffic that they normally had. So we decided, okay, we want to do something for our power users, and we want to kind of put ourselves in a little bit safer position. So for the last 8 months, my team has been working on building an iOS app and building an AMP-enabled website. Kind of smaller projects. We also built an Alexa skill, an IoT cooktop that connects with our app, and an app for a Samsung smart fridge. So we've been really busy in the last couple of months, and we've thought a lot about like what we want these products to be for our users, and we've been thinking a lot about like a digital cookbook or something that makes it like really easy for people to go back in and actually use these for cooking rather than just kind of like zoning out to them. So when we think about a cookbook and like what kinds of recipes are going to be around, like something like a chicken Alfredo pasta recipe, we're probably going to find other kind of creamy like pasta recipes within that. So we thought what we wanted to do was build a related recipes feed. And we could see from our own search data within the Tasty vertical that people in the same session would maybe like search pasta a couple times or search beef stir fry a couple of times. So when people are like actually sitting down to cook something, they kind of already have an idea of what they want to make. So by being able to like find all these related recipes, we can potentially make this like kind of exhausting search a lot easier for our users. And then the second thing that does for us is we know that the most highly trafficked recipe pages are going to be the ones that we have published most recently, but say our like recipes from 3 years ago are probably still, you know, just as good for when you want to make dinner. So this kind of gives us an opportunity to resurface older content and create some recirculation. So you might wonder, like, why do we even need to have a computer do this? Don't we have humans making these recipes that really understand our content better than our computer is ever going to understand? And I think we've heard this, like, anyone who's worked with metadata knows that human-created metadata can be pretty difficult. I think we've heard this like concept at a couple of different talks today. So early on, we were working on a project to categorize all of our different recipes, and we found out pretty quickly that humans are not very good at that, and there was some pretty like devastating stuff that went on in that. First of all, at BuzzFeed, I think we have had some issues with metadata in that previously when articles were written, the authors would say which part of the website it would go on, and they are obviously very incentivized to get as many views as possible. So one of the categories was just BuzzFeed that went to the main page. So obviously everyone put everything under BuzzFeed, and we had no metadata for those articles. So kind of after that experience, they were kind of trained to add as many tags as possible so that they could maybe maximize the number of views that their content could get. So we'd get things like teriyaki chicken meatballs would be tagged as breakfast, and I'd be like, okay guys, I don't know why you're eating that for breakfast, but that's not going to work for us. One of the like worst possible examples that I saw was we had a collection of mocktails which technically do not have alcohol in them, so a child could consume them, but I don't imagine there are very many parents that would want us to be like training their child to like crave a Moscow Mule. So these tags actually power a module in our app where we show kind of like collections of recipes. So a few days after we launched the app, this showed up, and my head just like kind of exploded. So we know that we're not going to like use the producer's tags. They're not going to decide which recipes are related, probably because they're just going to find all of theirs and say theirs are related. So we have to figure out some other way to take this recipe data and make it machine readable. So in machine learning, there are a couple of different methods for doing this, and two really common ones are dummy encoding and label encoding. So for dummy coding, what you do is you take your list of tokens, and each token becomes its own separate column of binary zeros and ones for whether or not it's there in that row. And for label encoding, you take your whole list and then you create a transformation of integers. So Tokyo becomes 2 in this instance, Paris becomes 1, so on and so forth. So both of these methods have the same kind of problem in that they don't really have an understanding of how similar an ingredient might be. So in our original recipe database that we created, I had about 12 different versions of Greek yogurt, like full-fat Greek yogurt or 2% Greek yogurt or just regular yogurt. So both of these would have like no understanding that these are really, really similar things. They would be entirely different integers or entirely different columns. And the process of going through and like merging these things is kind of complicated because at some point it does really matter if it's like a fat-free thing or like a full-fat thing. So like how deep do you want to go into these things? The other issue is label encoder implies some type of ordinality to your data. And really at the end of the day, there's no reason why a lime would be 2 and a lemon would be 4,000. So for kind of both of these reasons, I didn't really want to move forward with these methods. I did look into some more advanced methods like polynomial and backward difference and Helmert, but none of them really like solved any of these problems for me. So what I eventually landed on was deciding to create word embeddings. So when you have word embeddings, you can take a raw text corpus and create vector representations of the words in your corpus. So for this example, it would be eggplant in this array of decimals. So word embeddings, theoretically, when you plot them in an n-dimensional space, should have similar words end up spatially closer together and then dissimilar words farther apart. So in this kind of toy example, porpoise and dolphin and SeaWorld are kind of close together, but camera and Paris are kind of farther off to the side. There are a lot of different ways to make word embeddings, but they all kind of come around this same type concept of a word is characterized by the company that it keeps. You can create them using TF-IDF vectorization, word-to-word co-occurrence matrix, the most famous of which being GLOVE, which was created at Stanford. There are a bunch of different neural network implementations, but kind of the most famous one is word2vec, which was created at Google and originally published by Thomas Meekloff, which is like a 2-layer neural network. When I started researching this problem, I did find that both GLOVE and word2vec produce very high quality word embeddings, but that GLOVE works better with really, really large data sets. We kind of had like a medium or like artisanal sized number of recipes, so I felt pretty confident moving forward with word2vec, which is what we did. So just want to like give you a little overview of how word2vec works with the skipgram implementation. So first you're going to take a sentence like the quick brown fox jumped over the lazy dog, and you're decomposing this into context words and target words. So the and brown become the context words for quick and fox for brown, and brown jumped for fox. Then each of these words is initialized as a random vector of very small values. You're actually going to have a separate vector for the word as a context word and the word as a target word. And then you try to predict the context words from the target words using a softmax regression classifier. And continuous bag of words, which is a different implementation of word2vec, is just the opposite of that. You're trying to predict the target words from the context words. So after you make your prediction, it's ridiculous and terrible because it started completely randomly. So you're going to go back and make updates to your word vectors using your objective function and stochastic gradient descent. And then you just kind of keep doing this over and over and over again until you meet some stopping criteria, be that maximum number of iterations or minimum change within your vectors. This is just kind of what it looks like as a neural network. You have your input vector, your hidden layer, and then your output softmax classifier. So you might be wondering, like, how is this different from any other neural network? It sounds like pretty standard. Some of the things that word2vec did differently from the neural network implementations that came before that was this concept of word pairs and phrases. So things that are like very commonly together get treated as phrases rather than single words. The big example for this is Boston Globe. So Boston and Globe separately mean something very different than the newspaper. So the frequency that these pairings come up together means that they can be treated separately as phrases rather than single words. We also do subsampling in word2vec, so really frequent words become less frequent in your training examples. So this is kind of just like a slicker way than using something like stop words list and removing those things manually. Like we can kind of figure out what our stop words are in the algorithm rather than inputting a list. And then the really amazing smart thing that happens in word2vec is the negative sampling. So the larger your data set is, the more vectors you're going to have to update through each run. So instead of going back and updating the word embeddings for every single word, you're only going to update a small percentage of them. So you're going to randomly select some negative words to update, and then the positive word, which was the word that actually happened. So that's kind of how this is different, and it's a lot faster than the previous implementations. But so what do you do when you actually get these word embeddings? In the original paper by Miklov, what they had is a list of analogical representations that they understood very well. And kind of, for me, the easiest one to grasp was capital cities and their countries. So we had this like understanding of like Washington, D.C. and USA and things like that. But for food data, I don't really know what apple minus pear would be, or like banana plus orange. There's no like clear relationship there. So one of the things we did to try to understand if our model was doing what we expected was do some dimensionality reduction and visualize this data. We were creating 70-dimensional vectors, which obviously we can't just visualize. So there are a bunch of different ways to do dimensionality reduction, like PCA, linear discriminant analysis, t-distributed stochastic neighbor embeddings. And what we eventually landed on was using TSNE to make these visualizations. This is what you're going to see most commonly in papers about word2vec. And one of the reasons for that is it won kind of a prestigious visualization challenge on Kaggle. It's generally considered to be better for visualization than PCA, mostly because it solves this kind of like crowding problem. So you're going to get kind of a better like visualization at the end. One of the things that's really important to think about, though, when you look at these visualizations is that this is not a clustering algorithm. So when you're looking at it, don't read too much into cluster sizes or like how far apart they might be. And one of the reasons for this is that the hyperparameter perplexity has a huge impact on what visualization you're going to get out of this. So you could just like get something different every single time. This is really just like a sanity check, like is my model like doing anything at all that's useful to me? So this is, hopefully this will load, kind of initially what we got for our word embeddings for kind of our more popular ingredients. So we can see like all of our boozes ended up together, coffee and espresso are close together, and then we have like a little grouping of pastas up there. So we're feeling like pretty good about that, but we're gonna look at this from another perspective as well. So the other thing we can understand is like, we know as humans how similar different like ingredients or types of food should be, so we can look at the cosine similarity of these vectors. Just an aside, I really like this person's website, Data Aspirant. They explain all the different similarity measures through Kung Fu Panda. I don't know why, but I just think it's kind of adorable that they do that. So we're looking at the cosine similarity between these vectors. We kind of understand some of these things because we all are people that eat food. So looking at this cosine similarity of cake to torte, we can see that they're pretty similar, but cake is unfortunately very dissimilar to salad. Similarly, chocolate and ganache are quite similar along with cocoa, but guacamole is very dissimilar to chocolate. So now that we have word embeddings that we're feeling pretty good about, what can we actually do with them? So it turns out that word embeddings are pretty modular. When I first started working on this seemed kind of crazy to me that you could just take these embeddings and like add them up or subtract them and concatenate them and they could retain all of their data. The kind of classic example with the modularity of word embeddings is this example of king minus man plus woman equaling queen. So the idea that we had was that if we had all these word embeddings, we could add them up. We could just take all the preparation steps in a recipe, sum them up, and then that should represent our recipe. So that's kind of exactly what we did. Once we did that, again, we went back to TSNE to try to figure out if this was doing something that we thought worked. Here's kind of, like we've got our desserts down at the bottom in green, comfort food and healthy food is kind of mixed together because even our healthy food is not that healthy, and then kind of alcohol being in purple. And I know this is really small, but all the brownies are kind of ended up together and all the like drinks over here are together. So there's a bunch of different hyperparameters in tuning this model, but at the end of the day, my objective was for a module on our website to have kind of context-aware, like relevant recipes that would make sense to the user and wouldn't seem crazy. So I did make a lot of really hideous spreadsheets with a bunch of different implementations and hyperparameters for this. So I didn't really see much of a difference between the skipgram implementation or the continuous bag of words. And it didn't seem to make too big of a difference in terms of what similarity metric that I used. The biggest thing that changed in this was what we actually put into creating the Recipe2Vec. So to train the word embeddings, our only option is to use the preparation steps, because we need full sentences to have this like concept of context words and target words. But we can also just like throw in the list of ingredients or throw in the titles. What I found in the end was if you use the ingredients, you could find something that had a very similar like flavor profile, but it would be a completely different recipe. So things like peanut butter, like granola balls, would come out really similar to like a peanut butter smoothie. But at the end of the day, like a smoothie is very different from like an energy ball. So we stuck with just using preparation steps. So the way that we actually implemented this, here's like a little diagram of our architecture. We have a Python script that is sending off messages to our QR reader when either 12 hours have passed or a new recipe has been created that's either going to retrain a model completely or use an existing model. We pull down all of our data about our recipes from our MySQL database. We kind of dump that into Redis as our key value store, and then our API retrieves that and surfaces it back to our app and to our website. So we're using Redis, the Gensim implementation for word2vec, Python for all of our different services and scripts, and then MySQL for our recipes database. So we are publishing roughly 15 to 20 recipes a week. We just kind of like fit the stale model to it as soon as it's published, and then just retrain everything every 12 hours. And these are kind of the sample results. So we've got this like cheese stuffed meat thing, which is like a lot for me, but it's kind of cool. We found all the other like cheese stuffed meats. So before we had this project, we could have like, the best we could have done is like show other dinner recipes here. And now we've gotten into like a very specific type of recipe that I'm pretty happy about. Here's again some other example results for kind of like a cheesecakey type thing. Before we would have just shown kind of random desserts here or like high performing desserts, but now we can show like really similar recipes to here. And it kind of works across the board. Like it works for our stir fry, it works for kind of booze. There are like some things that we have to tweak in this. So there can be recipes that have like very similar preparations but very different purposes. So like here, our like meal prep smoothies are prepared very similarly to a pina colada, but obviously the idea of like drinking a pina colada versus like having like a healthy smoothie in the morning is very different. So there are like little tweaks that we do on top of this. Smoothies can also be very similar to soups, so we kind of like fudge a little bit of that, but in general, this feed is just straight like word2vec embeddings summed up with cosine similarity. And we've been really happy with it so far. We launched this website about 2 months ago, so at the time we needed something that wouldn't require any like feedback data from our users. So having this module like really helped us a lot. So in the future, we're hoping that we can use these Recipe2Vecs for a lot of other things, like predicting the performance of new recipes based on the performance of older recipes, kind of going back and creating more context-aware recommendations. So combining traditional collaborative filtering with our recipe similarity metrics. Right now we have some item-to-item and user-to-item collaborative filtering, but we don't surface it as a module on its own because we want to create some type of like cohesion in terms of like the groups of recipes that we're sharing. We can also use this for like making recommendations back to our producers for what type of recipes they should make in the future, and it's just like generally useful in machine learning applications. So that is the end. Questions? Also, we are hiring.
Recommendation systems are tricky sometimes, and what you're trying to optimize for in terms of user experience or metrics. Was that a factor
Similar in some other way, what do you mean?
I guess like make a full meal. Consider a recipe that has other recipes in a similar process.
So we chose recipes that were similar in their process and their end result, because what we saw in our session data for search history on our website is that people would be looking at similar recipes. We saw like pretty rarely that someone would like look for a side and a main and a dessert. Generally, like people were like looking for a dessert at that time, or they were looking for like an entree, and we saw less like full meal planning. We do see that change during tentpole holiday events. So around like Thanksgiving and Christmas, we do see full meal planning. But generally, people are kind of looking for like one thing to eat. Like especially our audience, like most of the stuff is like kind of like quick dinners. So they are not looking for like a full meal.
Talk about how you're retraining your model basically every 12 hours. Like roughly how long is that retraining process?
Just 10 minutes. So,
Your data set ballpark?
so we have like 5,000 recipes. So it retrains quickly. It's like, I don't think we actually really need to do it every 12 hours, but it's cheap and easy, so we do it.
Can you just cover again the difference between the continuous bag of words and the version that you did end up using? One is about context from target, and the other is the opposite?
Yeah. So skipgram is predicting the context words from the target words, and continuous bag of words is predicting the target word from the context words. So in continuous bag of words, it's a little bit faster. You're kind of in skipgram like artificially creating more data points to train on. So I actually didn't see too big of a difference in terms of the results of either of them. I think if I had a much larger data set, the efficiency would become more of a concern. But yeah, that is basically the difference. You just swap around whether predicting the context words or the target words.
You mentioned using this to like provide recommendations for like people that are actually like, producing the recipes. Based on the performance, how do you have any like ideas or thoughts on how to?
Yeah, so we create the video and the recipe ahead of time, so we can actually create the vector before we publish this and then try to predict how well it's going to do. So right now we could try to predict it based on performance on Facebook or performance on our website. So that's generally how we would do it.
You have to select the number of context words that you were going to consider when you're using word2vec, right?
That's right. There is like a default, but
Did you stick with the default? Did you notice any differences?
I played around with a couple different versions of the context words window. I didn't see like tremendously huge differences in them. So I think you're probably like pretty okay with the default. I think for recipe steps in general, like a smaller window probably works better because they're not really that long of sentences. I guess if you were like looking at a philosophy paper, maybe like a longer window would make more sense.
How did you curate your recipes?
So we create all of our own recipes.
Oh, you do?
Yeah, so we have people on staff in New York, LA, and Japan that are making these recipes. Actually, in the UK as well. Yeah, it's nice. They're like a floor below us, so they'll like send out a Slack message when they're done cooking, and people just like run downstairs and get the leftovers.
Oh, that's fantastic. So the idea is that these are easy to make?
Yeah, they're either like quick, easy to make recipes, or kind of like really beautiful ones. Like we have one that is like a cake that looks like the inside of a geode, or we have these cookies where you like they look like an aquarium inside because you like melt the candy. But then a lot of the other recipes are like, here's like throw this chicken on a pan with some vegetables and like you'll have dinner in 10 minutes.
Did you have to clean up the text at all?
There's like very little cleanup involved in this. Like I'd done NLP projects before where we were spending a lot of time cleaning and like removing stop words, but with the subsampling in word2vec, that wasn't really necessary. So it's actually like pretty easy.
To build off that question, how did you handle like the numeric information in the preparation steps, like oven temperature or certain sizes?
So all that stuff kind of got left in, and just like we like find the embeddings for that and add everything up.
So you mentioned that you would analyze within the session traffic and see
Mhm.
whether or not they're searching for similar types of meal.
Mhm.
For that similarity, are you basing on tags or are you basing on the similarity?
So so looking for similar recipes, we're looking at the repeated searches. So the actual text from the search that they're looking for. So then you're like chicken pasta, chicken bacon pasta, like that thing. So we had like kind of text similarity within that we were looking at.
The alpha model, I think, is used for putting good metadata back in institutes. You said that metadata was bad.
Oh yeah.
Have you considered implementations that use that, or are you just ignoring it?
Let's say so far I'm ignoring it, but it is like a thing that we need to do. We have like better metadata than when we started. We initially had this, we have like an editor that people can go in and select these tags. And we didn't have a limit on how many people could select. So now we just have a limit where it's like you can pick one occasion or two occasions or like one meal. So once we put in these kind of limitations, we saw like a dramatic increase in the quality of our data. So it hasn't been like a huge interest to us right now, but I think it's like something that I want to get back to when I have time for it. Yeah, I think that's what we're moving towards now. When we initially created this module for our website and our app, we're launching, so it was like, we have 10 users, which is us, so we don't really need their data. But I think the end goal of this is, yes, to kind of make like a blended model with like kind of a more traditional recommendation engine and this kind of recipe similarity.
Was it difficult to iterate through this whole process offline, and I hope that what came out with matched well with online results? Were you able to test this live at all?
Yeah, we just tested this live. Luckily we have some good backend engineers, and we were pretty set up to throw things on stage. So my team kind of is acting as like a separate kind of startup within BuzzFeed, but luckily BuzzFeed has really good infrastructure for deploys, so we just did everything on dev and stage, and then we're happy that it still worked in prod. Cool. All right. Thanks, guys.